Welcome, everyone. Thanks for being here. I am pleased to introduce Timothy Lucas from Pepperdine University, who's going to share with us about engaging students in differential equations with slopes. This is a really cool software. My students have all have it involved or installed on their phones, so we're very grateful.
Thank you. And thank you to the organizers for inviting me to share a little bit about slopes. Um, I'm going to get right into it. So slopes is it's an app that I've developed with a group of students and faculty at Pepperdine University. And it is available for both iOS platform and Android platform. It actually now works on desktops for Macs, because if they have the new M chips in it, it will use the iPad version. But this is the purpose of this was just to figure out how can I engage students in the visualization of differential equations, um, and uh, and try to help them to make the pictures without having to have a lot of software background. And so if you're interested, you can go to slopesapp.com. And you can get a link there, or you can search for slopes on one of those relevant app stores. And usually below about 2 or 3 skiing apps, you'll find slopes for differential equations. So I found when I was teaching differential equations that the students had a lot of obstacles to visualization. So when I first started teaching the class, I used to try to get them to use some sort of professional software. We would get maybe we would get like a volume license or something like that for something like Maple or Mathematica or MATLAB. But this was pretty expensive. And I found that the students really didn't want to use the software because there was a steep learning curve with the syntax and everything that's involved. I still think that there are great pieces of software, but for one semester, it was hard to get the students to draw the pictures that I wanted them to draw. So I used to appeal to free software. There are things like dfield and pplane out there, and you'll see pictures that are kind of inspired by that. But there became less and less support for Java, and so it was hard for the students to use that. And then I know that some of the things that you see can be done in GeoGebra or Desmos, but I kind of feel like you're working the system to try to get it to make the pictures that you want, with instead of having an application that's designed specifically for students to investigate differential equations. And then another thing that I really wanted to do was produce images that then we could manipulate easily. So that's why I decided to look at mobile devices for visualizing differential equations. I found a little study when the first iPad came out. Our university actually bought a bunch of them and said, hey, will someone try something in the classroom with these? And we did a study where we looked at students using iPads versus kind of using laptops for some work in a business calculus class. And what we found is that these portable devices, whether it be an iPad or even a phone, they have comparatively large screens, like versus things like graphing calculators and things. But they're highly portable, and they're easier to manage than kind of large unwieldy laptops. But most importantly, they have these tactile interfaces where you can interact with the graphs. And so we ended up publishing a paper about how iPads could be used in constructing collaborative learning spaces. And that ultimately was the genesis of me thinking, like, how could we create an app for visualizing differential equations? And then more recently, we ran a study that's published in Primus on how I use slopes to enhance learning in ordinary differential equations. So the students like their phones, they like using their phones for things. And so I felt like this was a device that was natural to them. And so we decided to develop for phones. So since semiote is a lot about modeling with differential equations, like I wanted to talk a little bit about how I approach my differential equations course. So if you open up a traditional differential equations text, a lot of texts, not all of them, but a lot of them kind of have this format where the very first thing they do is some sort of review of various concepts in calculus. And then they jump right into how do I solve first order equations? Like separation of variables, like looking at integrating factors for linear equations, doing exact equations. Eventually, like they get into things like existence, uniqueness, and maybe some autonomous equations and stability. But the equations solving the equations tends to be upfront, and it tends to be the emphasis, as if you could solve lots of differential equations. And then modeling all of a sudden comes in chapter 3. Now we'll talk about what these equations are used for. And that's not really how I like to approach my class. Instead, I want to start with the mathematical models. I want to like look at what are the physical assumptions that are involved in those particular models. Like, how do we turn those assumptions into mathematical expressions? And then all of a sudden we have differential equations. But then once the students have these differential equations, I have this kind of mantra about thinking before you choose to try to find a solution method. Like, let's look at what other things we can figure out. What kind of graphical analysis can we do? Is it slope fields? Is it phase planes? What's going on with equilibrium solutions? Can we determine equilibrium solutions and their stability without even having to solve the equations? Can we make rough sketches of the solutions without even being able to solve the equations? And then I start to think, after we've done all of that, we look at numerical solutions and analytical solutions. And I think that's what this app was kind of designed with, that progression in mind, where the students can explore the space first, and explore what solutions look like first, and explore kind of what the results are for these models before they look into, say, solution techniques. And so what I'm going to do is I'm going to talk to you about a model that I kind of use in my classes that's inspired by some local species to Malibu, where Pepperdine is situated. There's biologists that like to study the local amphibians. And so there's a problem surrounding the endangerment of this guy. This is the California newt, or Tarica turosa. And that newt has seen a lot of population decline in the Malibu creeks, and that is due to the fact that there's a lot of drought going on in Southern California, but also these invasive crayfish. And so crayfish were kind of introduced to the Malibu creeks probably a long time ago, 60s, 70s, when people were fishing they were fishing in the creeks, and they were using these crayfish as bait. And then when they were done, they were just like, well, crayfish live in water. Water's right next to me. And they just dumped out their buckets. And then all of a sudden, here are these crayfish that are supposed to exist in slow moving waters in like Louisiana, the Mississippi River. And now they've been introduced to the Malibu creeks, and they just multiply by like crazy. And so what I like to do is use the management of the crayfish populations as kind of an example to introduce all sorts of different models and differential equations. So it turns out that there are organizations that are trying to kind of clean up the creeks from these invasive crayfish. They love to eat all sorts of amphibian larvae and egg sacs and things. So they really want to kind of clean them out of the creeks. So they design these traps so that crayfish can kind of wander into the traps, and then they can't wander back out. And so it makes for like an interesting modeling problem, where you have we have a crayfish population. We can assume that it grows continuously, but then you've got people who are intervening, and they're trying to eliminate the crayfish population from the creeks. And so what I do in my classes is I kind of set up this progression of models, and you'll see how I interact with slopes with these models. But the very first thing that we look at in class, instead of instead of kind of looking how to solve differential equations, is we look at, okay, what are the assumptions of exponential growth and decay, right? Populations are growing proportional to the current population, or maybe we could have them declining at a rate proportional to the current population. And then we add like a removal term. So if we can remove crayfish from our system by trapping. So we add this constant rate of removal that's signified by B in that equation. So that's kind of a second step that we look at with the differential equations for my students. And then we talk about, okay, but obviously crayfish don't grow forever, so there must be some sort of carrying capacity, a limitation of resources. So we look at logistic growth. And then the model that actually we used in research when we were looking at trying to figure out optimal trapping schemes for the crayfish was we took a logistic growth model and then we subtracted a constant. Said like, what happens if you can remove a certain number of crayfish per month? And that was a good model when there were a lot of crayfish. But we also realized that if you reduce the crayfish population, you may not be able to hit that constant trapping each month. And so we looked at a second model where the rate of removal was proportional to the current population. So those are those last two equations there. And so I set up this kind of progression of models that we work through with the students and then use those to introduce different kinds of differential equations, things like linear and separable. And then eventually we do end up moving on to solving them. So okay, so I'm gonna open up the app. So this is slopes. It comes with 5 activities. I'm gonna mostly like look at the slope fields activity with you guys today. When you bring up the slope fields activity, it already has an equation loaded up so that you can see a slope field, but you don't have to use that equation. You can go in and edit the equation. I'm just gonna look at growth being proportional to the current population. So you can put numbers straight into the equation, but I kind of like to have a constant that I use. So I'll make a little growth rate. We'll make it maybe 0.2. And so I have students start by simply making observations about this slope field. What do you notice about the arrows? Okay, so I ask them what the arrows represent. What patterns do they observe amongst the arrows? When they're looking at the patterns, like a lot of times they notice that horizontally you don't see any difference in the steepness of the arrows, but vertically as you increase y, you see that the arrows are more steep. So they're making observations about that. And then I ask them, well, how do those patterns relate to the model and the differential equation? So eventually, usually they come upon like, oh, the differential equation doesn't have t in it. That's why we don't have any difference in the horizontally in the steepness of the arrows, right? But growth is supposed to be proportional to the current population. That's why the arrows are getting steeper as we increase increase y, our population. And then I have them start putting solution arrows on here, so you can kind of tap on the screen. And you can put solution arrows on there. You'll notice if you guys play with this on the phone, the table to the right here where you can adjust what the initial conditions are, like doesn't appear, but you can use the little arrows at the bottom to make that that table appear. And so they can make observations about how the solutions relate to the arrows. Okay, and then we say, okay, well, what happens? What's the difference between that and decay? A lot of times they give them a different model for decay that has to do with chemical decay, but they can make kind of the same observations. But in this case, they'll see that solutions are kind of decaying to an equilibrium value. And we even start asking, what is equilibrium for this system? Even though it's so simple, it's just 0. But then something that's fun is that we can introduce a new constant. We'll call it B, and that could be our trapping rate for our crayfish population. Okay, and so I'm gonna make this smaller to make it so you can see it. Maybe make this 0.25. So it's on the screen. Okay, and so now we make the same observations, like what's going on with the arrows. And a lot of the patterns are the same, but the students will eventually pick up on the fact that this picture is the same as the one that they saw without a trapping rate, except for that it's shifted. So there were solutions going up, but then the negative solutions, they were going down away from the equilibrium. If they add on that constant, then they'll see, oh, wait a minute, solutions are still moving away from the equilibrium, right? But the equilibrium has been shifted. Okay, and so that actually is their first chance to answer interesting questions that are come up in the research, which is like how many crayfish do you have to trap, say, per month in order for you to drive the crayfish population down to zero? Okay, and they can see that they need to have an equal or a trapping rate that's large enough so that if you have a certain initial amount of crayfish, it'll drive down the population to zero. And so these are the kinds of pictures that I tend to share or have the students explore. And then what happens is when we finally go to solve these equations, then the pictures, the things that they notice, the observations, especially the observation about shifting the equilibrium, like that informs their solution methods. So slides here, I kind of want to, if you'll give me a little leeway, I'm gonna rant a little bit, but it's kind of like it's a fun rant. Like I'm not gonna, everyone has their own style when they teach differential equations, and this is mine. So I like to say things a little sarcastically and in jest. So I hope that no one finds that too offensive. But I'm gonna rant a little bit about how sometimes when we teach differential equations. So here here's kind of the summary of the pictures, and you can see that we have the same graph when we shifted the equilibrium when we were subtracting crayfish. Okay, so a lot of times in these differential equations classes, you'll get to this first equation, dy dt equals a times y, and you'll solve it using separation of variables. And I think, well, why are you doing this? How is this helping you at all? What is this reinforcing about what this model means? And you're doing a lot of work, and in fact, some of it is notationally poor. And so why are we subjecting our students to doing this as kind of their first pass at differential equations, right? Why not instead make an observations about the fact that the solution, right, or the derivative is supposed to be proportional to the function itself. I guess if you were a little more advanced, maybe I was getting ahead of myself. Okay, so let's assume I asked the students a question like, what kind of function has a derivative that's a constant times itself? And a lot of times it takes a while. Sometimes the students will say like a polynomial or something, but eventually we settle on an exponential. And what I do is I have the students like verify that an exponential is really what's going to solve the differential equation. And then we play around with like, what if you added a constant? What would that do? Maybe multiplying by a constant. And through that experimentation of guessing and checking, we end up coming up with the right solution to the differential equation. And it seems like, why would we just kind of guess and check? Shouldn't we have some sort of direct method? But honestly, as you move forward in differential equations, like most of the methods, even up to some of the things that we do in partial differential equations, are just guessing and checking. And so I think that is something that is a skill that I think that they should be able to do. So I have them learn kind of how to solve this through guessing and checking. Okay, but then now let's change the equation. Like let's add the trapping rate. So we're going to solve an equation that looks like ay plus b. Well, we could do separation of variables again, but man, that's error prone and it's long and it just seems a little excessive. Integrating factors is probably better, but it still seems kind of excessive, like trying for this problem. But instead, if we use our intuition that was based on those graphs, we can say, no, let's solve this equation by again guessing and checking. We saw that the graph was just shifted up, So maybe all we have to do is add a constant to our previous solution. And if we substitute that back in, like we get something really cool. We get that the constant is the equilibrium solution. And so now they see that, oh, okay, so if I adjust this differential equation by this constant, if I add to it, right, the whole picture is shifted by the equilibrium. And so these models are all about either moving towards or moving away from the equilibrium. And so that's kind of that's the end of my rant about how I think we should start introducing these things. So you can actually, here's some questions. I'm sure that I'll be posting some slides and stuff like that, but I ask them things about like what happens, like solutions moving towards the equilibrium, solutions moving away from the equilibrium. We find out that the constant that we were looking at shifting by was the equilibrium. Okay, so then generally I move on to things like logistic growth. I'll just kind of look at slopes here, and you can type in the equation, but there are some models that are preloaded. So we'll look at things like logistic growth. Again, they can see kind of things are growing to a carrying capacity. Okay, and then we'll do an adjustment to that. We'll maybe actually I'll put the harvesting model in here. So we'll now have like what happens if we trap the crayfish and with the logistic growth. And what you find is, that's not big enough. Is that good? I think so. So you'll find that for some solutions, it grows to the carrying capacity, right? For some initial conditions, grows to the carrying capacity. But for others, out that it decays away from some minimum threshold. Which is kind of cool. And so then again, they can start making calculations about based on initial conditions, like how many crayfish would we need to trap to completely get rid of the crayfish population. But in fact, you can even you can make it so that you can get rid of the crayfish for any population, okay, initial population. And so what they can start doing is playing around with the model, like playing around with the trapping, and then kind of trying to see is like, oh, here, with this trapping constant, I've got two equilibriums, like one that's stable and one unstable. But if I increase trapping, I can make the equilibriums disappear. And so this is like their first look at bifurcations, right? So they can see that like, oh, if I adjust this parameter, like we can have a change in how the equilibriums behave. In this case, we had two equilibriums, one stable, one unstable. But if we increase our constant of trapping enough, it just makes the whole thing disappear. I took too long on a couple things, so I'm gonna just kind of mention that you can do some exploration of bifurcations. Again, seeing that like these two equilibriums, like if you increase the trapping constant, you can find the bifurcation point where there's one equilibrium and then they disappear. You can do this also with instead of a constant rate of removal of crayfish, you can do a proportional rate of removal. And then in this case, you end up always having two equilibriums because zero is always an equilibrium, but the equilibria switch stability. And so it's again another investigation that they can make that kind of leads them to those first concepts of bifurcations. So let's see, where am I? Okay, so I want to just show you two things, and then I want to leave time for any questions. I just want you to know that there's a phase plane plotter that exists. So you can, it comes up with a predator-prey system by default, but you can see kind of what the orbits look like in the phase plane. On the iPad here, in the bottom corner, it shows how the solutions vary over time as well, so that you can compare them. But also, if you're on the phone, you can kind of cycle through the graphs using the arrows at the bottom so that you can see both pictures. So there's phase plane stuff. You can plot systems of differential equations. I actually had this loading up the SIR model by default, and this was a choice that was made way back in 2017 before it was such a big deal. But I love pointing out, see that that green curve, that's the one we were trying to flatten. See, that was the flattening of the curve. And so but you can actually, you can add lots of equations. So you can do like up to 12 equations. And my students use this is kind of a model prototyping area when they're trying to do projects for my classes. So there's those things. There's some oscillations with second order equations, just little mass spring system thing that goes on. And then there's a numerical activity. So I just want to finish up real quick. Oops. And just say that like students' feedback has been good. When we've done surveys, they feel like slopes increases their understanding of mathematical models. I usually talk about some of these quotes, but they like how interactive it is and how you can visualize solutions. They find that that's helpful in class. I talked about the publication. And so I just want to acknowledge real quick that I had a bunch of students who worked on this with me, and they were very, very like helpful, especially Joshua helped me come up with the whole thing at the beginning. And then Jacques helped me get it on the phone from the iPad, and Alex Krieger helped me get it on Android. So that I always try to mention those three especially. But essentially, that's it. And I might